Hello, this is the Freshman Summer Resources video. It's on factoring. So, to start off, oh, did not turn off. Okay. To start off, right, why is factoring important? It's like basically the backbone of algebra. Like, you're going to be doing so much factoring. It's pretty fun, but don't get me wrong, but it's like really important to know. And it's really important because one example, which is really important, is solving for the zeros of any polynomial, right? So for the sake of example, say we have the polynomial x squared minus 5x plus 6 equals 0. I don't know what values make this 0. But if I rewrite it as x minus 3 as x minus 2 equals 0, it's really easy to see what makes it 0. Because if I input 2, I get 0, right? Because anything times 0 is equal to 0. Same thing. If I input 3, I also get 0. So that's why x is equal to 2 and 3 are your solutions. And even you can exercise, you can try this as an exercise, but they're the exact same things, you're just rewriting it, right? One form is nice because it shows me, hey, x equals 6, or y equals 6 is your initial value. Another form is nice because it shows that 2 and 3 are the roots. So it shows a lot of different information. And there's another form you'll do later on, which is vertex form, which gives the vertex and forms of it, but yeah. I actually should have probably mentioned that in the quadratics video. That was the one thing I forgot. But yeah, so going on, factoring polynomials, really important. So one way is factoring by grouping, right? And I'm not talking about factoring quadratics because everyone here already knows how to do that. That's why the last video exists. But factoring by grouping is important because it involves factoring polynomials with 4 or more terms. So say you have, so before I even go on to this, I'm going to show like why it's important, right? So you have this polynomial. You have x squared plus, so x squared times x plus 3 plus 2 times x plus 3, right? I'm just going to say, like, to make this easy to see, you can pull out that x plus 3 because let u equal x plus 3, right? So then you have x squared times u plus 2 times u, right? Then factoring out that u just gives you u times x squared plus 2, right? Which is just x plus 3 times x squared plus u, right? Because I made that substitution earlier, and then I'm making it back again here, right? So I'm just going to go over 2 examples of the problems so you guys kind of know what to, like, expect. So, yeah. So you have these 2, right? And I'm just going to do factoring by grouping for both of them. For the first one, you just kind of look for like greatest common denominators, and here you do it by grouping these 2 terms, right? That's kind of what the name suggests, right? So 2x squared is the greatest thing I can pull out, so you have x plus 3. 1 is the greatest thing I can pull out from this. So now this is just equal to 2x squared plus 1 times x plus 3, right? Notice how we pulled out that x plus 3, and now we have this quadratic. So now it's so much easier to find the roots of these. Same thing of this, right? You have x squared times x minus 3 plus 2 times x minus 3. Now you have x squared plus 2 times x minus 3, right? Same thing. Now I have this just by factoring by grouping. So it's pretty important. Probably try doing exercise on yourself for it. But yeah. So I'm going to enter full screen. So now, this kind of leads on to something called Simon's favorite factoring trick. So it's a trick that when you have problems, when you have 2 variables multiplied together, it's really nice because using, like, Simon's favorite factoring trick derives from grouping. So you can use it to solve for, like, integer solutions because you're just plugging stuff in. So I'm going to show you this by an example. And yeah. So you have this example. Pretty cool example. I'm trying to see how much. Okay. So you have this, right? And now, how do I factor this by grouping, right? You have xy plus x plus y, right? You need 4 terms, so I'm literally just going to add another term, right? I don't know what that term is, but I know that I'm adding it. So I'm adding it to both sides. Now, I don't know what that term is, so I'm just going to start by factoring by grouping on the first 2. So I can pull in an x, that would give me y plus 1. Now, I have y plus 1 here, but how do I make it a y plus 1? Well, I can just add a y, or I can just add a 1. So this is true. So now, factoring by grouping gives us x plus 1 y plus 1, right? This is the whole trick. Why is this important? Because it's so easy to find integer solutions for this. Because if x and y, and x and y are integers, then x plus 1 and y plus 1 are also integers, right? So now I'm looking for breaking down integer factors of this. 72 just goes into 2 cubed times 3 squared, right? 8 times 9, 8 times 9. So I'm going to make a chart over here. I'm going to make a chart over here of x and y. And say x plus 1 equals, can x plus 1 equal 1? This would be some solution, but no, because then x would equal 0, and that's not a positive value. So x is going to equal 2, y is going to equal whatever that, 36. So then x equals 1 and y equals 35, right? Because x plus 1 is equal, so you just subtract 1. And you can keep doing this. Say x plus 1 is equal to 3, then x is equal to 2. Y plus 1 would therefore have to equal 24, so y is equal to 23. Then what happens if we have 4, right? If we have 4, then we just have 36, right? No, wait, no, we don't. We have 2 times, we have 18, yeah. So we would have 3 and 17, right? And you can keep going on and find these. I'm not going to find all the solutions because there's a lot. But yeah, this is just the method you would find to find integer solutions. Sometimes it'll ask you find the sum of all possible values of x. That's one way. But yeah. So that's pretty much just Simon's favorite factoring trick. Now, common factoring identities. Memorize these. You don't have to try to memorize these. If you're doing math teams for enough, you'll just memorize these based off instinct. Because say you have x plus b squared. I already know, like, yeah, that's x squared plus 2ab plus b squared, right? And this just comes with practice, but you'll get the hang of these really soon. So you have all that. And these all are like probably the most important you'll ever need. There's obviously a couple more, but these ones are the most important. So yeah. And there's not much to it. These ones, you can like find a general solution for a plus b to the n power using binomial theorem, which if you're definitely interested, go research that. This video doesn't cover it, but yeah. So yeah, now we have my favorite part, which is the theory behind all this stuff, right? Because you can do the math, but if you know the theory, that's where the true math lies in, right? So the first important one is the factor theorem. This one we kind of already know, but say you have a, like being like a, well, I meant root, not factor. But yeah, I'm just going to change this to root, right, of the polynomial. Then the polynomial can be rewritten as x minus a times q of x, where it's a different polynomial that's also a factor. So, for example, say we have this polynomial. Then x minus 7 times some polynomial q of x is equal to x cubed minus 2x squared minus 29x minus 42, right? This all makes sense. And, yeah. So, that's a really good way of seeing the roots. So, that's a pretty important thing, just knowing if it's a factor. And you can see if a number is a root using synthetic division, which I'm going to cover later in the presentation. But, yeah, that's pretty much just a really important thing. There's not much to it. You just need to know that if something's a root, and why does this make sense? Because if we plug in 7, this whole thing is going to go to 0, which is supposed to, which is just true, right? Because when you don't write anything equal to, it's inferred that it's already equal to 0. So, yeah. Alright. This is a rational root theorem. This theorem states that if you have a polynomial, this is just a general way of writing a polynomial. This is written this way so it's broad enough. And you have the roots that are rational, where basically it's in the form where p and q are integers, and it's in the form p over q. Then p must be a factor of a sub 0 and q must be a factor of a sub n. And this is true all the time. You also do this subconsciously when you're also trying to factor a quadratic. I will show you the proof for this right now because it's pretty cool. So I'm going to say, starting off, let's say we have the polynomial a sub n times x to the n plus a sub n minus 1 times x to the n minus 1. And this is going all the way on to a sub 0. And that's all equal to 0, right? So that's just a general polynomial definition. There's not much to it. That's just a given. So now that we have this, what are we going to do? Well, we want to prove, so it's basically show that x is in the form p over q, where p and q are integers. Or wait, that's not the form. Right? They're in the form of integers. So you have that, and the best way to do it is let's just plug it in, right? We're gonna plug in x equals p over q, and if we run into a contradiction, then we know that we're wrong. But if we don't, if everything works out, then we know that we're right. So we have a to the sub n times p over q to the n plus a sub n minus 1 times p over q n minus 1. This goes on to, I'm also going to write the last term, or second last term, sorry. So a sub 1 times p over q plus a sub 0. That's all equal to 0 still, right? So I don't like fractions, and that's kind of true. So I'm actually going to just turn everything not into fractions, because also the other thing with fractions is it's really hard to find if something's divisible by something. So say if something's not divisible, then I'm going to multiply everything by q to the n, right? So we have a sub n times q to the n. So we're going to multiply both sides by q to the n, q to the n, because that's going to cancel all the fractions. So that's just, actually, I'm going to write that step here. Right, so that's just equal, so now when we do that, we get a sub n times p to the n plus a sub n minus 1 times p to the n minus 1, or wait, sorry, p to the n minus 1 times q, right? Because q to the n over q to the n minus 1 is just q, plus a lot of extra terms that we don't really want to do, so we're just going to generalize it. Plus a sub 1 times p times q to the n minus 1. Think of why this works, because it's kind of mirroring it. Plus a sub 0 to the q sub 0, right? Or no, a sub 0 times q to the n, sorry. So I'm also, this parentheses should be here. But yeah, we have this. Now, I want to show something is factorable, right? So I'm actually just going to move this term over to the other side, because I want to factor this, and I know p is a factor of all of this, right? That's why I want to split up. So I'm going to take out that p. That's just a sub n times p to the n minus 1 plus a sub n minus 1 times p to the n minus 2, right? And there's also a q attached, right? And this is just going on until I get a sub 1 times q to the n minus 1. And this is equal to negative a sub 0 times q to the n. So now, you're nearly done. And just so you guys see it, I'm just going to, let this whole thing, be thought of as multiplying two things, right? So I'm multiplying p, and I'm multiplying some polynomial, which we know isn't a factor of q, because there's no q that lies here. So because of that, I need a factor that works out. So this has p, and we know that p in q, we know that the greatest common denominator, so GCD, of p and q is equal to 1. Why? Because p and q is already inferred to be in the most simplified, right? So that just infers that, right? So because of that, p has to be when you multiply this, a sub 0 has to have a factor of p. So therefore, we've shown that p divides a sub 0, right? So we got that, and if you remember, p is supposed to be our numerator, right? Or yeah, no, p is supposed to be our numerator, so it's supposed to be a constant. And yeah, okay. So now we have to show that q works out, right? So basically, what we gotta show is that all these terms here have a q. So hypothetically, I could pull out a q, but I can't. Why not? Because this has no q, right? Well, at least that's what we think. It says it has no q, but we've already shown that these two terms have to have a factor of q. This has to point to something here, right? So because of that, we need to show that now this whole thing is divisible by q. And is it? Well, every single term has some q except for this term, but it's already divisible. So therefore, a to the n times p to the n minus 1 has to have some, has to be able to divide q. Or more specifically, q to the n. But I'm just going to say q, just because we don't know for sure if it's q to the n. So you know that, but p to the n has no q for sure. We know that because, remember, the greatest common denominator between p and q is 1. So therefore, a to the n must divide q. So q divides a to the n. And that is exactly what we needed to show, because then p over q must be in the form of some factor of a sub naught over a to the n. So there is our thing. So that's basically the whole proof. I know it's kind of long, but it's pretty cool. So once you get the hang of proofs, that's when you actually get to do the math. So yeah. So we can do some practice. I don't want the video to be too long, so I might just gloss over it. Okay. So the possible roots, let's do some practice, is, so we have the plus or minus the roots of, or the factors of 8, which is 1, 2, 4, 8, over the roots of 1. So we know that 1, 2, 4, and 8, positive or negative, must be a factor of this. You can figure out which one works and then work from there. I'm not going to do the whole problem because I also want to like go on to the next stuff, but yeah, that's pretty much like, we don't let, like, you can do the determine the possible roots or the rational roots on yourself. So yeah. All right. This, I think I accidentally made a duplicate of the tab slide. But yeah, synthetic division. So this is like the last thing I'm going to cover. It's kind of more like advanced, but you'll do it in algebra too. So basically, this is the last method you want to use because it's really long and like tedious compared to like other methods for factoring. But you can use synthetic division if you know your roots are rational. So this is kind of like brute forcing it, but this is kind of like shorthand for dividing a polynomial, right? By a binomial. So this is shorthand for like long division, like I said, but the method basically has you write your coefficient in a line and then plug in a root. And you add down and multiply across. If you get 0, then it's a factor, right? So I'm going to show this, right? You have this, right? So I'll just do the process for you, right? So you have the coefficients of 1, 2, 1, 1, and then you draw like a little like box thing, and that's for your like root. So I'm testing out if 1 works. And 1 is the only possible 1 and negative 1. So so first you move this 1 down. That's always the first step. This number over here is always going to be this number, right? So move it down. And the algorithm is multiply your root and your number over here. So 1 times 1 is 1. Add down, you get 3. 1 times 3 is 3. So you get this. Add down is 4. 4, and then you get 5, right? 5 is your remainder. And what this means is that this is shorthand for saying that, hey, x cubed plus 2x squared plus x minus 1 is equal to x squared plus 3x plus 4. Notice how we use these coefficients. And then, oh, well, what is this? 5. 5 is the remainder. And how do we write a remainder normally? Say if we have 7 divided by 4, that's equal to 1 remainder 3, or 1 plus 3 over 4. So using that same thing, it's just 5 over your binomial, which is x minus 1. Remember this, whatever makes that term 0 is equal to this. So that's true. And notice how since this is not really a term, it's like it's not a factor, right? So it's not cool. So yeah, that's pretty much remainder. Now say if it is a factor, let's test out, let's do some practice and see if we can factor this quadratic or this cubic. So I'm like gonna, instead of plugging in 1, I'm just gonna erase all this. and this is a step you'll have to do. You'll probably have to write this a lot of times. But I'll plug in -1. So you have 1, -1 is just 1. You have -1, 0. -1, again, 0. Oh, wow, 0. So that's just saying that x plus 1 times x squared plus x plus 0 plus 0 over x minus x plus 1. But we don't even have to, like, this kind of redundant. So then this is equal to, so this is us factoring it, right? And we know that this is a factor, right? Now, can we factor this further? Yeah, this is really easy to factor. So this is just equal to x plus 1 times x plus 1. And then now we have it. We know that the roots are x equals 0 and x equals -1. See how easy that was? Like, synthetic division seems hard, but once you do a lot of practice, you'll get the hang of it. And honestly, I don't think the problem set has enough problems to serve as good practice. So I'd honestly say, yeah, maybe consider that, like, you should, if you want to, like, get bigger, better at this, then probably do a lot of practices on, like, Khan Academy or something like that. But yeah, that's pretty much it. And we can even go back to this and try doing synthetic division on this for yourself. You'll have to try out a lot of it because it's basically trial and error. But yeah. So what do the numbers mean? This is like one last theorem. So after doing the division, you get a remainder. So I already showed what that means, right? But if you get 0, you get a root. So that's saying that f of that root is equal to 0. And if you, like, get a remainder r, then the number you plugged in, so here in this example, we plugged in 1. That means that if you plug in 1 to this polynomial, you'll get 5, which is actually really helpful. Because say if you need to find a large polynomial, you can just do synthetic division and it'll work out. So let f of x be some polynomial. Then, like, this is just the proof, right? Let's say if we have a polynomial f of x, I'll kind of just write this here. So f of x, we know, can be rewritten as in the form x minus a times q of x, right? Yeah, and then plus your remainder, right? That's just how it works, right? And this looks confusing because we're dealing with polynomials, but what happens if we were just dealing with numbers? Say we were dealing with, like I said, 7. That's equal to 4 times 1 plus 3. 3 is your remainder, same thing. Now instead of numbers, we're dealing with polynomials. So why does this work? Because the remainder you get is also the same remainder you get when you do synthetic division. But say we plug in a, f of a, that's equal to a minus a times q of a plus r. We don't even need to know what q of a is because this just turns into 0. So we're just equal with 0 plus r, which just means that f of a is equal to r. So nice proof, and it's really short, not as long as the other one for your rational root theorem, but yeah. So I know I covered over a lot really quickly, but this is all like the kind of like dipping your toes in the water. I think that's the saying. I don't know. But basically, like, it's the whole thing is like you'll be doing this for a lot of times, like even in algebra 2 and like beyond, right? And even like calculus, you'll be doing a lot of factoring. So being able to factor is really important, and knowing these theories sounds like, oh, why do I even need to know of it? But it's really nice to know because it gets you thinking less about just memorization and more about actually intuition, which is what math is about. So I'm probably going to post the problem set later today, or I'll post the problem set, I'll post the solutions later today. So yeah. But yeah, that's all.